Number 5. Reactance and electrical power.
In the last video, 3 devices which perform important roles in AC circuits were examined.
Capacitors, devices which store an electric charge in a dielectric between 2 plates, were presented. Inductors were also introduced. These devices store charges within a magnetic field. Finally, transformers were described. You saw how these devices, which are composed of 2 electrically isolated coils, can transfer energy from one part of a circuit to another through the process of mutual induction.
In this final video on AC fundamentals, the important concept of reactance will be introduced.
Capacitive reactance and inductive reactance will be explained. The differences among true, reactive, and apparent power will be described. Finally, the transmission of AC power will be explained.
Let's get started by exploring principles of reactance. Notice that the word react is found within the word reactance.
Reactance is the opposition of capacitance and inductance to an alternating current flow in a circuit. Before moving ahead, let's compare reactance to resistance. From your past studies, you know that resistance is opposition to current flow. The greater the resistance, the less will be the current for a given voltage. The value of a resistor is measured in ohms. This value is the same no matter what kind of a circuit the resistor is connected to, AC or DC. The value of a resistor does not change with frequency. That is, a 10 ohm resistor has the same resistance in a DC circuit as in an AC circuit, meaning that a resistor does not react to AC. But capacitors and inductors do react. There are 2 types of reactance for you to become familiar with: capacitive and inductive.
Let's examine capacitive reactance first, which responds to changes in voltage.
It is designated in formulas and equations as X sub C and is always specified in ohms. The 2 primary factors that determine the amount of reactance that a capacitor will have are frequency and capacitance. Let's consider frequency first. Recall from the last video that in an AC circuit, as the voltage changes both in magnitude and direction, the capacitor continuously charges and discharges over and over again. If the frequency were to be increased, the same charge would have to be moved onto the plates of the capacitor, but in less time. If the same amount of charge is moved in less time, then the current must increase. Taking this one step further, if the current is increasing, this must mean that any opposition to the current is decreasing. Similarly, the lower the frequency, the smaller the current will be. And if the current is less, this must mean that the opposition to the current is greater.
In either case, it can be said that this opposition to current presented by the capacitor is inversely related to the frequency. As one quantity increases, the other decreases by the same proportion, and vice versa.
Besides frequency, the other quantity that affects capacitive reactance is the value of the capacitance itself. The higher the value of capacitance, the greater the charge that can be stored, due to the larger plate area of the capacitor. Since a larger capacitor has larger plates, a greater charge is required. Since more charge flows during the same period of time, the current must be greater, and therefore any opposition is smaller.
So capacitance and capacitive reactance are inversely related as well. One way to demonstrate this is to compare the output of 2 different sized capacitors in identical circuits.
For example, a 4 microfarad capacitor and an 8 microfarad capacitor are each connected in series with 60-watt light bulbs. Assume that both circuits are connected across a 120-volt, 60 Hz AC source. Notice that both lamps light, but the one on the left, which is connected to the 4 microfarad cap, glows less brightly than the other. The current flowing through the circuit with the 8 microfarad cap must be greater than that flowing through the smaller 4 microfarad capacitor. You can conclude, then, that the capacitive reactance of 8 microfarads must be less than that of 4 microfarads. This inverse relationship can be expressed mathematically with this formula for obtaining capacitive reactance. X sub C equals 1 divided by 2 pi Fc.
Stop the program and complete activity number 1. When finished, continue watching the program.